Okay, thanks to the organizers for giving me the opportunity to tell you here a bit about the status of gamma ray astronomy, and a big thanks to Karl-Heinz for introducing the field so that really I can hopefully keep up with the time. So I want to say something about the status of gamma ray astronomy, the end of the electromagnetic spectrum, and I should really beforehand just make clear this is a very broad spectrum with a very or research field with a lot of results given, and this is really a very subjective, biased selection which I want to show you. But first, again, as the introduction, this is the cosmic ray spectrum as introduced by Karl-Heinz, and this also motivates what we want to do in gamma ray astronomy, but I have to excuse that we are going down, not talking about this energy, but we are going down in energy a bit because this is such a rich physics there, and even there lots of things are really not understood. So this is basically the energy range which we are covering at the moment with gamma ray astronomy instruments, and why we are doing this. I think this is something one has not to argue about. I think gamma rays, of course, are excellent tracers of acceleration side of these ultra-relativistic cosmic rays, so that we can really easily identify these sources, which we also, as we heard before, is really a bit more difficult by doing this with charged cosmic rays. So, but just to give you an idea also why this energy band of gamma ray astronomy is so interesting, I just plotted here just a sketch of the whole electromagnetic spectrum ranging from radio, optical, X-rays up to the gamma ray regime, and just showing you what are the major players here in this energy regime, as this time some function of E square dE by dN by dE, which means this is not just to show the structures, but it has also the advantage that you can, in this kind of plots, you can see the energy per decade, which is provided by decade in energy, which is then provided by these sources. Okay, this is something where you can see this is classical optical astronomy, where you have starlight, you have dust, but then there are these non-thermal components which are ranging from radio up to X-ray with the synchrotron radiation of electrons, where you need accelerated particles and a B field. But then it comes to this region of gamma rays, where you can see there we have first of all some kind of inverse Compton also from electrons and ambient photon fields, where we have with the microwave background we have ambient photon field wherever we want in the universe. But then there is this additional component where we're interested in, which are hadrons from pion decay, and these are only showing up in this energy regime. So if we want to identify sources of hadronic cosmic rays, we have to do this. We have to look at them in the gamma ray regime. So, but now this is, as I said before, this is really a very broad field, and I just blocked this into 4 different classes of particle accelerators, which means, first of all, you have just stellar types where supernova shells or supernova remnants are a typical example of. But then you have also this collective type where all different sources or processes in a collective way leads to gamma ray astronomy. This for star-forming regions or starburst galaxies, and also diffuse galactic and extragalactic emission. But then there's also what I call some kind of complex type, which are gamma ray binaries or microquasars, where you have this kind of 2 players which interact with each other and produce gamma rays. And then, of course, there's something which is black hole type, which is the galactic center with a black hole, or basically every AGN, where in this region, of course, these processes which lead then to gamma rays take place and allow us really to study a bit of these kind of sources. So this is a very rough scheme of identifying this, but you can see from this is really a lot of things which are ongoing there in gamma ray astronomy. But first of all, let me just give you a rough idea what actually the technique is. One could basically start with what is an ideal gamma ray detector, and actually there is one in space. What you need to have to identify gamma rays, you need to identify photons, and this we know from particle physics how to do this. You just make a veto against charged particles, and then you just let photons convert, or you measure directly the energy of photons, and that's it. Okay, this is something which you can do in space, and which you can do with a satellite, and which has additionally the advantage of a large field of view. But then there's also other techniques ongoing, and where you can just use a photon which produces an electromagnetic shower, which then produces Cherenkov light, which illuminate a small spot on the ground. And if you put a simple optical telescope in there, you can just measure these Cherenkov light flashes. But there's also, because we are talking about particle showers, and there are also charged particles produced which reach down the ground, and then you can really use some large water Cherenkov systems on the ground to identify photons and also distinguish them from charged cosmic rays. And just to show you, this are the instruments which are currently, or the major instruments which are currently online. So we have this satellite in space, which is the Fermi-LAT satellite. Then we have 3 big air Cherenkov systems operating, 2 in the north, one's on La Palma, the other one in the United States, so MAGIC and VERITAS, and the southern hemisphere, this is H.E.S.S. And since recently we have now complete such a ground-based water Cherenkov system, which is HAWC in Mexico. And I just want to show you briefly what actually a few of these parameters are. So as I said, I think would be the ideal detector would be something, this is this Fermi-LAT detector for measuring photons. But of course the problem is very imminent. I think this is clear. You have 1 square meter of effective area, and this costs $1 billion. And then if you compare this to the ground-based instruments, which have 5 orders of magnitude more the collection area, and this you get for a relatively cheap price. So, and I guess you will find no funding agency in the world which pays you a satellite which 10 to the 5 square meter collection area. And okay, but this is then, you can see also the other advantages what they have. They're these imaging air Cherenkov systems here, they have a very good angular resolution, although they have a small duty cycle, but okay, something compared to HAWC. What is not mentioned here is that they have a factor of 10 or even an order of magnitude better sensitivity, and this is why they have seen so many sources yet. So, okay, but let me see just a few of these scientific highlights. What concerns of surveys, of course, you want to get a complete overview, as we have seen also from IceCube, what we have seen from telescope array and Auger, and it's also what we aim for with gamma ray instrument, to have a complete survey of the sky, what is ongoing in gamma rays. Then I would say something about the imaging of cosmic ray acceleration sites, then okay, physics of pulsar and pulsar wind, and then something about the extreme variability of AGNs. I should say this is all experiments are contributing really a lot to the field just recently, and this is also why some people tell this is now the golden time of gamma ray astronomy. But let me start with surveys. Of course, this is a complete survey. The Fermi-LAT is producing this complete survey of the sky, and they have just recently published the 3rd Fermi catalog, which is out. So this means, which is hard to see here, there are more than 3,000 sources. There's a significant fraction of extragalactic sources. There are many galactic sources, as you can see here, and this makes here the life from the experimental point of view very hard, is that they are confused with diffuse gamma ray emission, and perhaps I will mention this a few times during my talk, but more often, especially in the region of the Galactic Centre. I think there are so many diffuse components and so many unresolved sources that it's really hard to tell what actually is going on there. And I think we are all eagerly awaiting a publication from the Fermi collaboration what concerns the Galactic Centre here. But now this is then overlaid now is the status what we have with at TeV energies, not at GeV energies, but at TeV energies. Here you see that there are these spots on the sky, but there's also very dense population of sources in the inner galaxy. But now I will say you how complete, in quotation, the survey is, what we actually have. Just to show you, this is sky at TeV energy. If we are looking on our Milky Way, you see all the dots here, which is the current galactic very high energy sources, means in the TeV energy range. And this is basically the sensitivity, just an indication of the sensitivity of the current instruments for sources at a level of 2% of the Crab Nebula, which is the strongest gamma ray source which we have in the sky. So there you can see that we really have still a way ahead of us just to get more sensitivity, to get a more complete overview. But I just want to show you this one, the HAWC Observatory, which has just been inaugurated in March this year, which is then 20,000 square kilometers covered with this 300 water Cherenkov detectors. As you see, the picture which I've taken here is not very complete. Now everything is complete. And what they're really doing with these instruments, just from the shape of the shower really imprinted on this water Cherenkov detector, they can distinguish the photons or electromagnetic shower, one should say electromagnetic shower, from hadronic showers by just the shape of these events which they detected. And this is something in gray, what you see here. This was actually with an incomplete detector. You can see the coverage with the half and the and how the gamma ray scale looked like for them. You can see a part of the galactic plane, and now just recently they have just shown on a conference this update on this, where you can see already with this instrument that we start to see the gamma ray sources. But I should also see what concerns sensitivity is just that they're, as I said before, compared to imaging air Cherenkov detectors, I think this is just a factor of 10 worse. But they have this large field of view, they have this large duty cycle. So I think this is also in a few weeks from now at the ICRC, we are expecting really new progress results from them. But just to show you, to indicate where this region here, what we have seen actually is, and this is basically what they have reached here, is now this point here, that they have just covered this part of the Milky Way, and we have to see what the future will bring. There's another interesting region since many years in gamma ray astronomy, and for northern telescope, which is discussed, is the Cygnus region, and there has been a scan by the VERITAS air Cherenkov system, and this is basically in this direction, this region here, which they have really covered. And this is then the survey of the Cygnus region. They're not published as a survey paper, but they're published in BID, and they are just sources are newly resolved. So you can see this result, a few years old result from the Milagro experiment, which was the predecessor of HAWC, which was a smaller water Cherenkov system, and they have seen this, okay, what I call just a blob, this thing, and this has been now mapped more in more detail by VERITAS, and there you can see that this is most probably here a pulsar wind nebula, here a pulsar wind nebula, and here some star-forming region. You see that there is really some complex structure going on, and of course this is now the task also for the coming years to better resolve, to better identify what is actually ongoing here. Okay, this brings me to the H.E.S.S Galactic Plane survey, which is at the TeV energies, the most complete survey we have. But just as an indication, this is this region of the Milky Way, and also you can see all the depths which we have achieved with this plane survey. And this is now here the result we have. We can see here full sky, which is the Planck CO map, and you see this inner region, this white rectangle here. This is the H.E.S.S survey region. Okay, just for comparison, this here in green, this is the VERITAS Cygnus survey. You can see here this much larger survey we have, and this here is one with the outcome of the survey, and where you can see all these dots are all the sources, and you can see also there's some kind of diffuse component which is in. Just to comparison, this is the observation time here at certain dots. The white ones are 300 hours, but this in total, these are more than 2,600 hours. It took us 10 years with the current instrument to achieve this complete survey, and I should really mention that the speaker next to me, Werner Hofmann, is really basically responsible for this success. And you can see here, this is just one example of these, what the sensitivity we have achieved. The aim was 2% of the Crab Nebula. Most of the region we even reached 1% of the Crab Nebula, and this is, as I said, the most complete survey we have. And this is just one part of this, where you can see here all the sources showing up, and this we found 66 very high energy sources plus 11 complex sources, for example supernova remnant shells, which are then which are excluded from the automatic pipeline. It's the first time that this survey is analyzed in this with this kind of automatic pipeline, and this gives us this number of sources in the galactic plane. And this is something where the H.E.S.S collaboration is now about to publish this, so that the plots, although it is preliminary, the plots are basically final. Okay, but just one remark, when I just say this is the indication that we have this complete survey. I think there is one part which is also very much incomplete, and I could not resist to make this very small remark. Okay, this is just from a H.E.S.S point of view. If we look at our very close neighborhood, and if we are talking about positron access, about electron spectra, we are only talking about our very close neighborhood, the 100 parsecs around us. Because electrons lose their energy so efficiently that the sources of these electrons can only be nearby. And I just draw here this on this region here. This is where we are, and this here in red, these are possible gamma ray sources where, for example, Vela we have seen for monogen has been identified, this is for Geminga has been identified, and there is expected to see a result from HAWC at the ICRC in a few weeks from now. So you see, this is by far not an isotropic distribution of sources, and we have to identify these sources and map these sources before we can really tell what this positron axis is coming about. This is what we call the astrophysical foreground, and as Sam Ting yesterday mentioned, there is this pulsar, this model based on pulsar means pulsar wind nebula, means supernova remnant component. There's lots of things ongoing in our close neighborhood, and this is something I think a task for this gamma ray instrument really to sort out this question in the coming years. But let me come to this one, which was for many, many decades this belief that the sources for galactic cosmic rays are supernova remnants. I put here in an X-ray image, and this is where you can see the shock wave here outside, where this diffuse shock wave acceleration takes place. And I just want to show you where we actually are, what the picture is, and what we can contribute here from the gamma ray instrument. But let me start with this first image of a supernova remnant in TeV gamma rays, which is now a bit more than 10 years old. When with the H.E.S.S instruments here, you see in color, you see the gamma ray emission in black. This is an overlaid X-ray image where we have seen the first time a shell of supernova, a shell of gamma rays of a supernova remnant. And just to show you the progress, this is how the picture looks today, with this, and after more than 10 years of continued observation, where you can see all this structure, and this is for sure a clear proof that this diffused shockwave acceleration takes place. And this is the question is still whether these are electrons or hadrons, but it's for sure that this diffusive shockwave acceleration is the process which they are accelerating these particles. And this is not only this one here, there's the many, this is here in gamma rays, we see a few of these shell-type supernova remnant, and they compare very well with X-rays, where these X-rays are for sure coming from electrons. Of course, there is if an accelerator is accelerating protons, there will also accelerate the electrons, which are accompanying the protons here. But just to show you an overview of what we actually say and how we can actually distinguish, or whether we can distinguish, one has to look at the spectra. And this is here some compilation of spectra produced by Stefan Funk. And where you can see there are all this number of supernova remnants which are now detected in gamma rays. And this might look a bit confusing, but you can get a bit more of these, understand what's ongoing. Because when we are talking about a supernova remnant as an accelerator of cosmic rays, we are not talking about an LHC, which you switch on and you get a 14 TeV center of mass energy all the time when you have collisions. But this is something which is a dynamical evolution of this accelerator over time, and this is just an indication here what this might be. These ones here down here are very young supernova remnants. These are young ones between 1,000 and 3,000 years old, and these are very old ones. So this seems to be, and this, although it's not really conclusive, it seems to be that there is a trend that we see a time evolution of these supernova remnants here. But then there are just for two of these, which is W44 and IC443, the supernova remnant. There's also made a big step forward that we hear in the spectra by Fermi. You can see that there's here this, and see, of course, I should not forget that. Yeah, Marco, please forgive me. This is then, because there are also the dots in there. You can see that this is here by Agile, and also by Agile's right, that they see here this breakdown, and this is coming up that this is here basically the onset of pi zero production and pi zero decay, where we see the gamma rays from. So this is the clear proof that these accelerators, or these supernova remnants clearly are accelerator of hadronic cosmic rays. So this is then on one side, just to come back here, this is basically on this side, we have proven that these are hadronic cosmic rays. But the other question is, of course, we all the time believe that these supernova remnants are responsible for accelerating cosmic rays up to the PeV energies, up to the Ni, as been shown by Karl-Heinz in his presentation before. So this means at this range here, and we still have seen no of these supernova remnants or of these sources as Pevatron yet. So, but this brings me to the Galactic Centre, and here with the Galactic Centre, you can see here, this is the sky map of the Galactic Centre from the H.E.S.S experiment, where you can see here a very clear, a very bright source, but what you can also see is that this is a very, very complex region with a lot of diffused emission here, other sources here around. This is a pulsar wind nebula, some other sources here, and this is what the H.E.S.S collaboration now has done. They have now disentangled really the spectrum from the inner source here and subtracted this from the diffused region just around this, and what they have seen is that, what we have seen is that the intrinsic gamma ray spectrum here, well, we say this is the overall spectrum, but you see this here in the red line, which is the intrinsic gamma ray spectrum, has a strong cutoff at 7 TeV energy. As you might have this from just a source, it produces up to a certain energy, and then you get a cutoff, because then this is the accelerator is currently running out of steam. But then, if we look what is remaining there, is that the spectrum of this diffused emission shows no indication of a cutoff below 25 and follows a power law up to at least 50 TeV. And this is something which you see, because we have, if we see this more larger than 50 TeV, then you have just a factor larger particles at this accelerator produce. So this is an indication of a central source accelerating protons to energies larger than 500 TeV or even PeV energies. So this is something which is very interesting, and I just can only advise you just to follow what is ongoing within the next few weeks here with this regards here. Okay, but this brings me now to the extragalactic sky, and there I just want to show you just a few examples, maybe 2 examples, just to show that we need this instrument right now to see what is ongoing and this transient extragalactic sky. A lot of stuff is flickering around there, and then what we can actually see by surveying some extragalactic galaxies. So just what concerns time variability, there has been this remarkable result out of IC310, which is an AGN, which has a black hole size of 23 minutes size. And what they actually have seen in a flare in 2012, a few hours, which you can see here as time, they see here this outburst of gamma ray emission from this AGN, and this is with doubling time scale, which is of the order of 4.8 minutes. So this cannot be just simple shock acceleration in the jet, which cannot be just double on this very short time scales. So this is the possible explanation. This even what they have seen here might be a cloud or a star falling into the jet. So this kind of the events which then produce this outburst here, or that there might be a smaller subjet structure which is producing this this emission, or that there's plasma or accretion turbulence on a polar cap vacuum. So I just want to use this on this indication where you see a model or a picture how this could look like in the region around the black hole, and that you have this then here just on this polar cap. This is basically a similar mechanism which is taking place at pulsars, and there you can see here this very short time emission of this AGN, and it's clear that we need instruments which are online basically all the time to identify these kind of flares, because these flares are not, we cannot just order them, we have to look for them. The other thing is, I think, also a very nice example. This is also from this blazar here, which is also just remarkable because this is close at z equals 1. This tells us something about the transparency, transparency of our universe to gamma rays, because there is, of course, just by gamma production or annihilation, there is some process which just limits our event horizon which we have. And I think this is also really a nice example to be shown here on this conference, because this is really general relativity in action. There is something, the blazar is here, you have a mass distribution in between and Earth here, and what actually has been observed is that this AGN is then showing some outbursts by just looking at the light which followed this path here. And then, of course, this is everybody what knows this, and then one can really switch on the alarm clock, and 2 weeks later, the light from this path should have arrived, or should arrive on Earth, and this is actually what they have seen. As you can see here, this is some indication here. It's hard to see. There is some overshoot here. This means they get a signal from this AGN. It was also seen by VERITAS. They have launched several ATELs, and this really makes it easy so that in case we see an AGN which is then gravitationally lensed, that we can really prepare the instruments to look in this region when then the light from the other paths arrived on Earth. But then also for this very distant AGN, we get new constraints on the extragalactic background light. This means something that, as I said, we learn more about the opacity of the universe, and we need these instruments online all the time again, just to watch for these flares, especially for these extragalactic sources. But there's another I think very interesting result which came out to us recently, which is then the scan of the large Magellanic Cloud, which is also the cloud, this galaxy accompanying the Milky Way, which has been then observed for more than 200 hours by the H.E.S.S experiment. And by just looking, what you can see here, the large Magellanic Cloud, by just looking at the galaxy more or less at whole, there has been really the sources have been identified, and this, of course, what we actually see here is just the tip of the iceberg of what is going on in other galaxies. Everywhere we look at, we find gamma ray sources and of varying type. Okay, this is clearly just an indication where this is. This is southern territory, so this cannot be observed by the northern observatories. And this is just the first glimpse where we have seen a pulsar wind nebula, where we see a very powerful one, which is even more powerful than the Crab Nebula. Of course, it's the distance which makes the brightness we see so low. But then there are also the other thing with it. We have first time that we see a super bubble in this process. As I said, these kind of complex types, which then produce these gamma ray emissions here. And additionally, of course, what has been published there is that there is a limit on the gamma ray production on the supernova SN87A, which should start producing gamma rays right now and is permanently also observed here. Okay, but then the other point, which I said, with the pulsar wind nebula, if you have this relativistic winds around the pulsar, we can directly look at pulsars, what is going on, and there in very high energy gamma rays, there's also been made some progress. This is a very hot topic since the Crab has been detected by MAGIC above 20 GeV, and now this is that there has been the second pulsar seen on the ground, which is the Vela pulsar, where you see here the phasogram with this very nice peaks, and then down here from H.E.S.S, what is the energy distribution as seen by the instrument, where you can see, okay, it's hard to see, but this is at 30 GeV. So we have now instruments on the ground which operate in standard operation mode without any dedicated settings, which can observe down to 30 GeV, which makes clear that we are really closing the gap to Fermi, that we get a really an excellent sensitivity over a very broad energy range. There has been a continued observation also of the Crab Nebula by VERITAS and MAGIC, and this is on the most recent phasogram by MAGIC, where you can see there's even some bridge emission between the two peaks, and there has been even a claim that they see pulsed emission up to several hundred GeVs, and this is clearly challenging pulsar models to explain really where this emission is coming from. And then there's just recently, VERITAS has published an upper limit on Geminga. So it's clear some kind, although we're talking about two of these pulses on the ground, it's still some kind where we see with time, I'm really expecting that there will be also a lot of progress in the future and a lot of surprises. It has been documented by the Crab Nebula that it's not only close with what we actually see by Fermi, but just let me make a remark that pulses, of course, are Fermi-Lat territory. There you can see the dust distribution of pulsars, which has been detected by Fermi, with this lots of surprises, and especially what concerns the millisecond, what Hélène Lafont called the millisecond revolution, that we get the fraction of millisecond pulsars, means old pulsars which are powered by accretion. So this sometimes they are called these recycled pulsars, and this is really an ongoing fraction. And we have to see, I think it's just a matter of time when we see the first of these millisecond pulsars also on the ground, also in the region of several tens or several hundreds of GeV. So this brings me to my summary and my conclusion. I think the gamma ray experiment offers today a unique view on the high energy universe, and this ranges now from MeV to PeV energies, as was promised really long time ago, and we deliver unprecedented data of high precision. And this is resulting really in an increased understanding of the astrophysical foreground. I think many things I could not mention due to lack of time, but it should also be clear that we just see the tip of the iceberg. And I think although I end here with a complete view of the gamma ray sky by Fermi, it's clear that we're at the ground. We have to do a lot more, and I think this is just a bridge to the next speaker, to Werner Hofmann. Thank you very much.
Galaxies, because so far it was done by people like we had done at MIT, treated like gravitational plasmas. They are not anymore. So,
now, I think you're absolutely right. I think there are what is called this Fermi bubbles, this large scale emission. And okay, this is I skipped this because I'm working on a ground-based instrument, and this is I think this is really up to people from Fermi to do this. But of course, you're absolutely right. It was a big surprise. And
another point, if you don't mind, is that your community is discovering later you don't need only shocks to accelerate particles. We learned from the Voyager, that they crossed the termination shock. There was no particle acceleration. There are other mechanisms that now you're beginning to visit something like.
No, also here, I think also here what concerns the, although I was talking in the context of supernova remnant of diffusive shockwave acceleration, there are other acceleration mechanisms which play really a lot of role. So for example, if we take other thing from Fermi, if you take the Crab flares, gamma ray emissions, so gamma ray flares from the Crab Nebula, which cannot be explained by diffused emission, they need magnetic reconnection and all this other stuff. You're absolutely right, yes. But I think I should underline, I think the data which is now about to be, or is been taken or analyzed and published by this instrument, really something which helps this kind of models. This is clearly a data-driven research field, and we are currently discovering new things, and the quality of the data really is constraining models a lot. So this is really an enormous progress we made.
You pointed out correctly how important it is to look for nearby sources. But I was just curious about one of the slides you have shown in which there was a quark without sources.
Yeah. And I have to apologize for this because this plot we made for H.E.S.S, it just was the H.E.S.S field of view.
Okay.
On the other side, there's also a lot, but I just have not a complete plot of this. But I just wanted to show this plot based also on the discussion we had yesterday. I think it must be very clear that in our local neighborhood, it's anisotropic distribution of sources, and we have just a first idea what these sources could be. And although we have also seen that there are model calculations which very well describe a positron excess in a model, but they need some more experimental input to really constrain this model whether these are really pulsars.
Yes.
I think this is really an important task for the gamma ray.
Very important. Yeah.
I would like to remind that there are different information coming from TV, for instance, from Milagro, as you mentioned, and Argo, but also in the south from IceCube. The high statistic of muons permitted to study the TeV anisotropy, and indeed, if you overlap the north and the south, there are already some remarkable clustering at different energy range, and because of the statistic of muon tracking in IceCube, this information is quite rich and quite surprising somehow.
You're right.
I would like to remind that the TV most surprising to me is around the Vela. There is in the south a quite interesting clustering around the Vela.
But okay, this is right. But you meant that's what IceCube has really published is just a cosmic ray anisotropy in this energy range. How this is related then to data from the gamma ray experiment, we have to see. I think we have to see. I think if you just look at the Fermi data, okay, the correlation is not so clear. And for the ground-based instrument at TV energies, I think the sky coverage we have is just incomplete. We do not have an extragalactic survey yet, but I think this will come with the next speaker.
Okay, let's thank again Christian for he managed in half year to express the whole field.